So, in the last lectures we discussed about what is the influence on water particle kinematics on velocity variation and the flow field variations by interference caused by the cylinder, which is blocking the flow of field, wave field. We have also seen what is the influence of current on the given velocity profile variation along the depth. We have also seen the secondary vibrations caused by the system or a cylinder, kept horizontal, kept vertical, what we call as the characteristic dimension of the cylinder in the wave approach angle, and we understood that how the water particle kinematics gets altered, and subsequently we have said that how this alteration or the velocity variation can be captured to understand the force reduction on a given member by simply putting an outer perforated cover on an inner shield of a cylinder, so that the force in the inner cylinder is reduced, which can be considered as one of the effective method of retrofitting or rehabilitation of the given inner cylinder, provided the inner cylinder is not replaced because of its damage, but only put an encapsulating cover outside the cylinder, so in a specific zone which is damage caused by the splashing effect or corrosion effect. So, now in all these cases one is actually interested to ultimately get through an important point. When I have, let us say, water particle kinematics known for a given wave field, as an engineer one is interested to know what will be the force caused by this wave field on the given member. Usually cylindrical members are used in offshore structures. Because of many reasons. Foremost reason, it has got uniform characteristic dimension, which is nothing but the diameter of the cylinder for all wave approach angles. That is the one reason, foremost reason. The second reason is, if you look at the method of analysis, let us say look at the plastic analysis or LRFD, load resistance factor design method, circle or circular shape has a decently higher number of shape factor. That is the second reason. Those who know the limit state design or plastic design, you know what is the importance of shape factor in estimating the load carrying capacity of a given section. So, it has got a higher number. Third is the fabrication and precast construction is faster with cylindrical cross section, because we go for a seam welding. So, the connections become rigid and well established using a weld connection, and for of course transportation, erection, launching are easier with circular cylinders. So, cylindrical cross section is generally used in offshore structures because of many reasons, fundamentally this, and remaining all are ancillary reasons why they have been used, and therefore we use cylindrical cross section. Now, one is primarily interested what would be the effect of the wave field on the interfering cylindrical member in terms of its forces. Therefore, Morrison equation came into play. Morrison actually suggested an empirical equation on the basis of experiments conducted. Way back in 1950. So, it is a way back paper 1950 which is based on some experiments conducted by a team of people on measuring the forces on a cylinder which is exerted by the wave action on the cylinder, and is given an equation which I will write now, which we famously know, but still we will write down that. The general equation suggested by Morrison is like this: f of z comma t is Ci Vx dot plus Cd Vx, which can be written in two forms. This is called Fi, this is called Fd, this is called drag force, this is called inertia force, where V is the velocity in V dot is the derivative of the velocity which is acceleration. Both are water particles, where Vx is the velocity of the water particle and Vx dot is the acceleration of the water particle, and Cd and Ci are called drag coefficients and inertia coefficients respectively, which has to be estimated based on the experiments conducted by the team of people supported by Morrison. If you look at this equation carefully, the component of Ca has got two subcomponents into it. Now, Ci has two components, namely one is arising from the hydrodynamic mass and the second is arising from the variation of the pressure gradient within the acceleration fluid, within the accelerating fluid particles. There are two components. So, mathematically Ci has got two components, one is Cm plus other is Ca, which can be Cm multiplied by plus rho A, which I can write as Ci Ca actually is the inertia term, which consists of both the pressure gradient variation, where Ci is the inertia coefficient of the section, Cm is the added mass coefficient, A is the cross section area, of course rho is the density of sea water, and d is the diameter of the member, essentially cylindrical member. Call this equation number 1, that is equation number 2. Hence, force per unit length of the member is given by Fi x of t, which is Ci, not x of t, it is z of t. Z is the axis along the vertical, Ci Vx dot, which is Cm plus Ca Vx dot. that is the inertia force. Now the drag component Fd for unit length of the member, the drag component is given by half rho CD diagonal. And of course the drag force, the drag component heavily depends on the Reynolds number. Now looking at equation 1 implies that the drag force has a nonlinear component due to the multiplication of the velocity component. This has to be linearized, which actually makes the drag force nonlinear. So this makes the drag force nonlinear, which need to be linearized. Many researchers attempted this linearization and they are given an alternative. One can ask a question why linearization is important. I will come to that point slightly later once we understand how to linearize this. For a linearization coefficient existing, the force now will be given by a different expression, which will be, let us say, Cm Vx dot, which is CD bar Vx. There is no multiplier of Vx again here, which of course will have the pressure coefficient Ca Vx bar, because there are two components available in the inertia force, plus CD Vx absolute Vx minus CD bar Vx. So okay, the meaning of the equation will not change compared to equation 1. It is the same. I will call this equation number, this is number 3, I can call this equation number 4. If you compare 4 and 1, the meaning of the equation 4 and 1 does not change, except that I have added and subtracted an additional term, which is CD bar Vx. I will explain what CD bar is, because this term was anyway expanded from equation 2 and this equation was reproduced from equation 4 with substituting 2 in 1, you get from equation 4 like this. So compare 4 and 1, it is one and the same except two components are added and subtracted to make it balanced. Now I can rewrite this equation slightly in a different form. Rewriting, F will be given by now Cm Vx dot plus CD bar Vx, because I want to avoid the nonlinear part, plus Ca Vx bar Vx dot plus E. The E is interpreted as an error function. The term E in equation 5 is interpreted as an error function, which need to be minimized to make the equation accurate, which need to be minimized. Now if you look at the error function, which is component of, because this term is present, this term is present, this term is present, so it is a component of this, which is again a function of CD. Okay, so I have to minimize the error function with respect to CD. So minimizing E with respect to CD. error function. In fact, I should say CD bar because I am minimizing respect to the new linearized dark term. It is a linearized dark term because there is no nonlinear term available here. The original term is this, which has got nonlinearity. It is a linearized dark term. We presume that one function of this order exists. It is an assumption. Okay, so we minimize it with respect to that assumption, which is given by negative 2 of, there is a negative term here, time average of, the symbol indicates time average of CD Vx square CD minus CD bar, let me write this, minus CD bar Vx square. I must set this to 0 because I am minimizing the square of the error function. Once you do that and perform the operation of minimization with respect to CD bar, you will get, let me call equation number 6. We can get we obtain CD bar as CD of time weighted average of CD Vx square Vx by Vx. I mean all are small v, please, all are small v x square. Of course, this is also time weighted average. Equation 7. So, I get CD bar because it is equal to 0, 2 has no meaning, and I am looking at a time weighted average, negative will have no consequence on that. Okay. So, I try to find CD bar from this straight equation like this. Now, interestingly, you see, if you really wanted to find out the value of CD bar with a linear drag term, I must try to find out the time weighted average of this. So, I have to compare really the velocity square from the original process of the wind velocity. So, I must know what is the nature of the wind velocity process itself. So, generally the wind velocity, generally let the process be Gaussian. It is a Gaussian distribution, generally it is Gaussian distribution with a 0 mean process. In that case, you got a great advantage. The Vx square will be actually equal to the sigma square of the process. We can even call this sigma Vx square, make it very clear. And the absolute value of Vx, the mod value of Vx between the time weighted average will be an approximation of 8 by root pi. Now, can you tell me what is the value of 8 by root pi? The square root of 8 by square root of 8 by pi. Please change. What is the value of this? 1 point? Yeah. So, it is linearization. Instead of square, we are having 1.569. So, it is not actually equal to 2. Now, when you multiply Vx square with Vx, you get sigma Vx cube root 8 by pi. Okay. Now, here you may ask me a question, how are we eliminating the non-linearity term by introducing a higher order of sigma Vx. Now, sigma Vx actually is a number for a given process, okay, whereas Vx is not a number, Vx is actually a velocity term which is time weighted average, okay, it is a time weighted value, whereas this is a constant value for a Gaussian process. So, cubing anything is not a problem, simply a number, okay. So, simply cube this and multiply this with root 8 by pi. Therefore, CD bar now will become, hence let me call this equation number, let us say 8. CD bar now becomes, substituting back, CD of, let us say 8 by pi sigma Vx cube sigma Vx square, which will give me 8 by pi sigma Vx of CD. Of course, CD is there here. Call equation number 9. So, if you presume that a linearization of drag term exists, it will be a multiplier or some weighted factor of CD, which is given by this number, whereas this is not 6Vx, this is sigma, okay, which is known to me for a given process being Gaussian and zero mean. We know this, okay, for the velocity. And I think we all know how to compute this. If you got velocity variation or water particle velocity variation horizontal for a given wave field for a specific time domain, you can take a mean average of this, find the standard deviation and variance of this easily for a given statistical process. Okay. So, it is easily obtainable for a given Gaussian process. Once you know this, I can use this for linearization, get the value of force, which now will become, hence, linearized Morrison equation is given by f z of t Ci Vx dot is an acceleration term which includes Cm and Cv, both Cm and Ca. We already know, you refer to equation 3. Ci is a component of two things, plus Cd root 8 by pi sigma Vx Vx. So, one is the velocity term, other is the acceleration term. So, inertia and drag components. It is a linearized equation, there is no nonlinear term in this compared to 1. Let us call this equation number 10. So, 10 is a linearized equation which has got some approximation with respect to nonlinear original drag term given by Morrison, but this is necessary. Now, one can ask me a question, why the drag term has got to be linearized, what is the problem? Now, we have seen how it is linearized, we have derived it, we know the value, but let us quickly see, ask a self question to understand why a nonlinearization cannot be handled as it is. Let us take for example a complaint member. Let us look at the drag force alone, which is half rho CD dia V minus x, okay, x dot V minus x dot, okay, where x dot is the velocity of the structure or the member and V is the velocity of the water particle in the horizontal direction. And this term can also be called as relative velocity, we can call this as VR, the relative velocity, because system is also now compliant, the member is also now moving, therefore I have to capture a relative velocity term. If you expand this term and maintain the sign because of the mod on only one of this, you will see there is a square term and a product which will not be able to, there are square terms available at V squares, which is velocity square, structural acceleration square, and the product of V and x which will become nonlinear, which cannot be computed, because x dot is not known to me, is the solution of the problem actually. Because the equation of motion has got the displacement as the solution, therefore velocity and acceleration are not known to me. Okay. So, initially you cannot evaluate this term provided you have got to assume this, okay, and keep on iterating. When you iterate, when you have got a nonlinear term, iteration becomes combustible, it is very difficult to iterate. Okay. So, I want to linearize this. Compared to this of power of 2, I have got 1.569 as we pointed out in the previous minutes for example. So, there is an approximation available here, but this term is relatively easy. Okay. Here the variable is of course velocity and acceleration, but if you solve the displacement in the equation of motion, you will be able to get this. Okay. That is the beauty in this problem. I will come back to this slightly later, how the right hand side of the equation of motion is coupled with the left hand side. So therefore if you do not know the velocity and acceleration you cannot solve the equation of motion to start with. We will use Nemax beta method etc. later. I will show you the scheme later, but anyway this term does not have any non-linearity in its evaluation process as you had there in terms of compliant system. So it becomes easy, okay. That is the reason why we linearize this. Suppose if the force is on this about a vertical cylinder, if you have got an inclined cylinder then you have got to resolve the forces along and across or along and normal to the cylinder and find the respective components of the force in the respective directions and try to develop a vector in all 6 degrees of freedom, okay. So if the member is inclined with respect to the water particle approach angle, then you have got to find the velocity and acceleration or the force in general. One is tangential to the member, other is normal to the member, and you have to find the equivalent components of them in all 6 degrees in terms of relative degrees of freedom and fill up the whole vector. Though the force may be acting in one direction, since the member is inclined, now you will get forces on all respective activated degrees of freedom, okay. That is the idea. The second part of the lecture we will focus now on how do we get earthquake forces on offshore structures. The second part now is to get earthquake forces or seismic forces on offshore structural members. As we all know, when you talk about the force, it has to generate from a velocity or a motion of the body, because the force of the vibrating system is essentially from the motion displacement, okay. It is a very clear idea even in the case of water particle or the force exerted by waves on the member, there is actually no force, it is only the movement of the water particle which causes force, okay. It is actually the displacement of the water particle which has got, since the displacement is continuous in a time history, it has got a velocity and acceleration that arises to a force which we just now calculated and computed using a Morrison equation. So displacement gives rise to the force and so on and so forth. Similarly here in earthquakes also, earthquake actually is not a force, actually it is a displacement which causes the force. Now we are very clear about this idea how displacement can cause a force. Just now we saw in Morrison equation, when the water particle displaces it generates velocity and acceleration, when the cylinder interferes the flow field it generates force on the member, and the cylinder is also vibrating, it will give a secondary force which we say radiation etc. In the last lectures we know how the displacement can give rise to a force in a fluid medium. Same concept in earthquake. Now earthquake gives forces through its displacement. Now the question is which is getting displaced. In the earlier case it was water particle or the member, in this case it is neither of them but the ground, okay. The ground is getting displaced. So the ground acceleration which is caused during an earthquake results in the development of force. So one can ask a very simple question and try to understand how serious it is. Let us say I have one cylinder which is fixed, another cylinder which is anchored using a cable. Obviously system is designed so far that the buoyancy force will exceed the weight of the system, okay. Therefore, we will try to push the system up, because buoyancy we know it will act upward, weight of course will act downward, we know that, okay. So when the buoyancy system exceeds the weight of the system, obviously there is always an upward motion given to the body when it is put in water, maybe it is partially immersed, okay. Of course the buoyancy force depends upon the circumferential area of immersion and the depth of immersion, what we call as design draft, okay. It immerses, therefore it pushes the body because weight is very low, right. Since the weight is very low and the body is being pushed up all the time, we always need a cable which is in tension to pull this body down, otherwise the body cannot be held in position, the body will get afloat, body will be thrown out from the medium, because the buoyancy force is extraordinarily high compared to W. That is the design concept. One may ask me a question, why this design concept is evolved, what is the reason. The moment you keep this design concept on, commissioning, installation, towing, transportation, everything is very easy, because weight is compromised on buoyancy force. Simply you float it, you drag it, it will drag. If it would have been other way, it would have been very difficult to install this, Okay, that is for installation purposes. Then one can ask me a counter question, why for installation purpose design has evolved. That is the beauty in offshore structures, because in offshore structural schemes installation, commissioning, decommissioning is about 80% or 70% of the cost of the structure itself. It is very expensive. Therefore, we should have a mechanism. There are very special equipments, cranes available. There is a weather window within which you have got to operate, etc. All consequences are there. We already vaguely know this, at least what are the forces coming on. Therefore, we must, to facilitate easy erection and commissioning, towing and launching, we must have a system which is having excessive buoyancy by design, number 1. Number 2, this will also enable flexibility to the system which is required in the design for deep water systems. Okay, but this is a fixed system, so rigid, flexible, or what we call compliant systems. Okay, in both the cases, if I apply an earthquake force, what will be the consequences? Now, since the cylinder or the member is fixed to the bottom, obviously when the sea bed in this case, okay, moves, which is displacement, which causes an acceleration in all the 3 degrees, x, y and z, all the 3, okay, because earthquake forces will apply, or the displacement will apply in all the 3 axes. Okay. So, let us say it is happening in all the 3. Since this member is rigidly fixed to this, whatever forces offered by the system will be transferred as stress to the member material. If the member is able to take the stress, the member will not fail, otherwise the member will fail. Okay. So, it is actually a design concept in terms of adding this as an additional force to the member. Okay. Whereas in this case it is different, you see here what happens here. When an earthquake force is applied in this case, since the member is not resting on the seabed, practically speaking this member should not be influenced at all by an earthquake happening at the bottom, because the depth what you are talking about is approximately about 1000 meters. So, we talk about an acceleration happening at the bottom 1 kilometer below. We should not rather bother about this, because the member should not be influenced, because 2 factors. 1, it is happening at a very far epicenter from the bottom. Number 2, there is a good amount of hydrodynamic damping available, the water body, which will try to pressurize this and control and compromise this or disperse this force, which will not reach the member. This is the idea originally till 70s. Okay, people thought this will not be a force acting on the member, because the member is far away from this. Now, there is a very interesting concept here. The interesting concept is, since Fb is less than W, so Fb should be equal to W plus something to equalize this. That something was nothing but the tension in the cable. Okay. Now, the stiffness matrix, the mass matrix, or the variable submergence because of the added mass in the mass matrix are all unfortunately functions of T naught, which will derive later. Okay, all functions of T naught. Now, let us see what happens to this idea in this problem here. When the earthquake is applied at the bottom, since the tether is connected one end to the ground, which is moving, the tension in the tether is changing, because the tether is actually inaccessible or inextensible. It is an inextensible cable, strictly speaking. So, when it moves, because of the length variation caused by the movement, the tension has got to change, because tension is AE by L. Okay. When the length changes, AE by L will change, because K will change. When the tension changes, your stiffness matrix will change. When the stiffness matrix changes, the frequency of vibration of the whole system will change. Okay. When the frequency of vibration of the whole system changes, it may get into a mode of resonance with the wave. Okay. Therefore, tether tension variation is indirectly an accelerated problem because of earthquake force happening at the bottom, though it will not affect the superstructure directly, as in this case. Okay. So, this is more serious, one reason. 2, the second reason is, when this extension or displacement is very large, there is a possibility that the cable get pulled off. When the cable get pulled off, the floating member will have a stability problem, because this equation will no more be met. Okay, it will not be balanced. When the cable is pulled off, there is no T0. When there is no T0, system is having a over buoyancy design, the member will be thrown off from the seabed automatically. So, stability will be a problem. When it is thrown off or blew off from the position, the topside facility which is holding this will all crash. So, earthquake movement will cause indirect effect on the top side and the member, though there is no direct connectivity between the member and the ground. Is it clear? Whereas in this case there is a direct connectivity. Now in this case the advantage is, since the system is not designed for over buoyancy, the weight will always compromise this effect. Therefore the effect of the ground activity or the ground motion on the superstructure is insignificant mostly. Whereas in this case it is significant because of two reasons. One, the system itself is very compliant in nature. Second, it is affected directly by the T0 variation, which is affected subsequently by the displacement of the seabed. Okay? Therefore in both the cases displacement gives rise to the force. So as we saw in the previous case in wave, we need to have a spectrum, because there we had Pearson-Moscow spectrum, ISSC spectrum, modified 2 parameter PM spectrum, which we have seen all equations in the previous modules in the wave forces. So similarly earthquake force also we have seen the spectrum, which is given by Kanai-Tazimi. Of course Kanai-Tazimi spectrum is not directly implied upon for analysis of offshore structures. Kanai-Tazimi is actually a spectrum generated for studying earthquake motion on land based structures, okay? But here the extension is done. So spectrum suggested by Kanai-Tazimi is used for analysis. So let us see what is the spectrum. Yes, U double dot G, U double dot G, that is a classical way of writing a spectrum, because even in power spectral density function or even in wave spectrum we write S omega omega, okay. In this case omega is given by this is a spectrum which is given by Kanai-Tazimi for working out the forces, where S0 is called a constant representing the site characterization indicating the strength of disturbance. Omega g is called characteristic ground frequency, which is usually 5 to 6 pi radians per second. Nu g is called the damping term, which is the characteristic ground damping. It is usually 0.6 to 0.7 for hard layer. So this constant is known, this ratio is also known, omega g is of course known. So the entire spectrum is a function of omega, okay, which can be plotted, which will typically look, I will show you the figure in the next class, but anyway let us look at the reference. This was given in 1957. Semi empirical formula for seismic characteristics of ground, bulletin of earthquake engineering, Institute University of Tokyo, University of Tokyo, 308 to 355, no 325 sorry. Kazemi, a structural method of determining the maximum response, of a building during an earthquake, proceedings of Second World Congress, of earthquake engineering, Kyoto, volume 11. So, this is what we have, the Kanei-Kazemi power spectrum given in the year 1960 by both these people. We will talk about the basic assumptions used by these gentlemen in estimating the earthquake forces, the maximum earthquake force on a given system. We will take up a simple example and try to solve and show how this force can be computed using the spectrum easily. Then we will move on to the classical structure like articular towers, etc. Any doubt in this lecture? We have discussed about two issues here. One is the drag linearization. We showed you how linearization can be done and why it is necessary in a given system. Second is how to compute the earthquake forces caused by the ground seabed movement or the seabed displacement in terms of this power spectrum given by Kanei and Kazemi, which is known as Kanei-Kazemi power spectrum, which is essentially applied for buildings, but nevertheless recent studies in offshore engineering has used this spectrum for calculating the forces in the given members because of seabed movement. Okay. So, there is a very interesting homework for you to undergo, that let us try to find out what is the maximum disturbance caused to any one of the offshore platform in the recent past because of earthquake. Okay. There is a very interesting history available in one of the platforms in offshore, which had a very close epicenter in Gulf of Mexico, which was disturbed highly by the earthquake caused in the recent past. So, try to find out which is the system or which is the platform which is disturbed heavily by the recent past by earthquake signal at the seabed, then you will really appreciate how this system was actually done.